Hello students. In this video we'll discuss about the translation process of phases, whatever we have discussed in previous video. So that is phases of compilation. So in this video, how the input high level string will be processed individually. What is the input and how it is going to be changed after the lexical analysis. So what is it, how it is going to be given as input to the syntax and how like that. So this high level language statement, whatever we have taken, so this how these high level language statement will be converted into this machine level language statements. We'll discuss of each and every phase, right? So first let me start with the lexical analysis. So the input to the lexical analysis is A equivalent to D plus B star C. So the lexical analysis is also called as linear analysis, scanner. So like it is going to scan the input string character by character. And if this character is satisfying the regular expression of identifiers, then it would be treated as lexeme. And if it is satisfying the regular expression of any one of these, then that could be treated as lexeme. But before treating it as a lexeme, you should go for the maximum length. Means, for example, if I take like this, see A. So whether A is satisfying anything, A is not a keyword, A is not an operator, A is not a special symbol, so A is an identifier. But don't take it as a lexeme directly. Go for A equivalent to. Is A equivalent to is an identifier? No. Keyword? No. Operator? No. Special symbol? No. Numbers? No. So it is only A is satisfying the identifier. Then we can say that it is a lexeme. So which regular expression it is satisfying identifier, right? Then the token we should give it as ID. Same way equals to. First check whether it is satisfying the regular expression of these tokens. So these are the general C language tokens. So equals to is satisfying what? Operators. But don't take it directly, go for maximum. Equals to and D. Two characters are satisfying any? No. Then only equals to is satisfying the operator. Then what we can do here, you can take it as a lexeme. So equals to is a lexeme and what it is? Operator. Same way ID is satisfying what? A lexeme identifier. So the lexemes are nothing but the smallest logical unit in our program. Lexemes means what we have written. See, A is written by the developer, equals to is different. So lexemes mean the actual characters which are satisfying the specified tokens. These are defined by whom? The developer of C language, Dennis Ritchie. So tokens mean generalized classes. Lexemes means actual characters what we have written. And it is treated as identifier like that. So the A plus B star, A equivalent to D plus B star will be treated as ID operator, ID operator, ID operator and ID. So this one will be converted into these stream of tokens. So this is called stream of tokens. And this will be given as input to the next phase of the compiler. What is it? Syntax analysis. Now the syntax analysis will check whether this stream of tokens are syntactically correct or not. So they are lexically correct. Now we have to check whether they are syntactically correct or not. How can you check it? A statement is syntactically correct or not means if this stream of tokens can be parsed from this grammar, then we can say that it is syntactically correct. Means for this stream of tokens, if you could able to construct the parse tree, then it is syntactically correct. Of course, this can be converted like this. How a parse tree is generated from the grammar that we have discussed in the ALC subject, that is Automated Languages and Computations. So there you can, if you are lagging and if you don't have any idea, okay, no problem. When we are discussing about parsers individually, we'll discuss about all these things, right? So then the parse tree is constructed, then we can say that it is syntactically correct. And this one will be given as input to the next phase of the compiler, that is semantic analysis. So the semantic analysis by using SDTs, it verifies whether the statement is meaningful or not. As I told you, the main aim of semantic analysis is verifying whether all these IDs are type compatible or not. For example, if this is int, the remaining all must be integers. Like that, it is going to decorate this parse tree based on this type, like integer, integer, shortened, like that, and it verifies by using the SDTs, syntax directed definitions or syntax directed translations. So once it is verified, that semantically verified parse tree will be given as input to the intermediate generation. Right? That IR means intermediate representation generation. So guys, listen here. The output of this is in terms of ID operator, but for our convenience, I'm taking this A equivalent to D plus B star. So actually, we'll get like this. But for our convenience, I'm taking in place of ID equivalent to ID, just I've taken A equivalent to D plus B star C just to tell you which operator exactly it is, right? So, but actually you can write it with the ID like that, but it would be very easy once we are generalized like this, okay? So the intermediate representation represent the code either in three address code or abstract syntax tree. We have discussed about it, right? Directed acyclic graph. There are so many forms of IR, but the most popular one is three address code. The name is itself indicating that every instruction should have at most three addresses, at most three operands. It should not have more than three. It may have zero operand, one operand, two operands, three operands, but not more than that. But here we are having how many operands? Four. So this is not in three address code. So if you give this code as a input to the intermediate representation generation, where it is using the three address code, what it will do, it will store every sub expression in a temporary variable. So what is the first sub expression? B star C will be stored in T naught. You can see that. So B star C will be stored in T1. Okay, first variable. That's your wish, starting from 0 or 1. So the first B star C is stored in T1. Then this T1 will be added with the D. So D plus T1 will be stored in another temporary variable. So now how many operands we are having? 3. Like every sub expression will be stored in a temporary variable. So then we can write A equivalent to T2, right? So here the targeting variable is A. So here we can take it as A. So we can take the targeting variable as A equivalent to T2. So here we assume that this is T3, but you don't need to do it. We can write directly A equivalent to T2. But see guys, here how many operands? 3. How many operands? 3. How many operands? 2. So at most 3. So 2 also allowed. And this will be given as input to the next phase of the compiler, that is IR optimization, where so this A equivalent to T2, right? T1 B star C, T2 D plus T1, and A equivalent to T2. So in place of T3, you can assume T2. Now see, we have to reduce the code either in terms of cost or space or time, but we should not disturb the three address code and we should not disturb the function of this. So what we can do, see, we are performing the addition and again we are storing in T2. Then immediately we are copying the T2 value to T3. So instead of these two, we can directly write A equivalent to D plus T1. So where A is treated as T3, right? You can directly take A equivalent to D plus T1. See, whatever the task and whatever the intermediate form we are having here, so it is going to perform the same task and it is going to be in the same intermediate representation, that is three address code. We have reduced the number of instructions. So this optimized code will be given as input to the next phase, that is code generation. See guys, as I told you, the code generation main important thing is register allocation. So we have to find the minimum number, but of course I'm not worrying about the minimum number now. So assume that A is stored in R1 and B is stored in R2. Assume that R3 is dedicated to the C and R4 is dedicated to the D. But generally we have to find the minimal, but okay, just go for it. So first what we have to do, B star C. So first storing the B in dedicated register, C in dedicated, and performing the mul with R2 and R3, that is B star C. The result will be stored in R2. then storing the D in R4 and adding with the result of B star C where it is R2. So just performing add, it's not null. So add R2 comma R4. So we are adding the result of B star C with the D. This is D and this is B star C. Then what will be happen? The result is stored in R2. So then this result whichever is stored in the R2 can be directly stored in the A, or first we can store this R2 in the R1 and finally we can store the R1 in the A. So this is how it is going to be converted into the targeting code. So but the problem is guys, listen here. See R2 and add R2 comma R4 means the addition of B star C and D will be in this R2 again. Now what is R2 is having? D plus B star C, that is in R2. Now why again we are moving R2 to R1 and R1 to A means R1 is dedicated for the A. But what is the need of this redundant statement? You can directly write like this: move A comma R2 because the result is stored in R2. So instead of these two, you can write in one. So this is called machine dependent optimization. You can write directly move A comma R2, right? See guys, listen here. Instead of storing the result from R2 to R1, instead of storing the result back from R2 to R1 and R1 to A, you can directly write this R2 to A so that we are reducing one instruction. And where we are applying this optimization in target code, that's why we are calling it as machine dependent optimization. Okay. So that is about the translation process of compilation. So in the next video, we are going to discuss about major data structures in compiler.